Okay, so hello everyone. I'm Youssef. I am the team leader of the Grand Prize winning team, and I will be presenting our ink detection part. This is the part that I worked on, and then later Julian's going to present the tomato and the automatic segmentation and the auto segmentation stuff in general. So let's get started. So before the Vesuvius Challenge, there have been a lot of work on ink detection before, and I would highly recommend that you dive into Stephen's PhD thesis because it has a lot of gems in there. So the work of Professor Sears' lab basically brought up this idea of you can take a fragment, which is a piece of a scroll, a small piece of a scroll. You can do this segmentation pipeline such that you get like a 3D image, like a 3D object. And then you can train a deep learning model to take small pieces of this image. This image is usually like a couple of thousand pixels by a couple of thousand pixels. So you can take like pieces of this image and train the model to predict whether this like cube, the small part has ink or not. And then when you slide this window over, you get like the ink with the writing that is in the fragment. And we knew this works, and this was kind of like the start of the ink detection Kaggle competition. So this is where I first saw the Vesuvius Challenge, and Kaggle ink detection worked on 3 fragments, and 1 fragment was in validation. And the key findings from the Kaggle fragments were the majority of the solutions used what's called a unit architecture. And we're going to discuss this in a bit. 4 of them used like a ResNet 3D, and 2 used like a SegFormer solution. And a lot of these ideas come from video classification and like activity recognition field. And this was sort of the direction where I went to look after the Kaggle ink detection competition. One of sort of, if you read throughout like the top the 10 winner solutions, and I have for a very long time, you will notice that almost all of them had like used heavy augmentations because you had like a limited amount of data, and the augmentations were both spatial and also depth-wise, and this allowed the models it allowed like the contestants to prevent overfitting. Overfitting still happens, but you know it takes a bit harder, and also the performance is a lot better. The vast majority of models also operated on like a 256 by 256 pixel or 512 by 512, and this was kind of the inference window for the majority of the models. And most of the models also optimized for the dice score. Some only used like only cross entropy, but the dice score was also the metric for the competition. So optimizing for the dice score is not a bad thing. It's a little bit different for the scrolls, and we're going to see why. So the unit architecture, it's called that because it resembles the letter U. And you can think of it as 2 AI models. One part is an encoder. It tries to find like relevant features in an image. It tries to look at the image and see, okay, I see this pattern here, I see this pattern here, and passes like this information at different resolutions to the second part, or the second AI model, let's say, which is the decoder. The decoder takes this information and tries to piece together how the output image should look like. And you can think that the decoder pretty much does a classification problem, like it's trying to predict whether there is ink or not in the grid, but it does it on a grid so that you get like the 2D output image. So this is the progress timeline and also the agenda for today. So I'm gonna take you throughout the journey of how I like went first to try to find like the first couple of letters, how I like took these couple of letters and got to the first letters, and how we went from like the first letters to the grand prize. So like July, August, I did a lot of self-supervised learning experiments, trying to get like to that spot where letters are starting to show and the model is not very shocked. September, I did like a lot of fine-tuning and this iterative labeling, and I also did like overfitting optimizations, or like countering overfitting. In October, I won the first letters. That's when the announcement came out. And then from October, it was scaling up, trying to replace Inception 3D, the model I use, with a more powerful model, doing like data enhancement iterations, which we'll discuss in a little bit. And the grand prize ended in December, which we won, as you know. So after the Kaggle ink detection, when we had like very good models for fragments, however, these models did not really translate for the scrolls. When you look inside of the scroll, the model was sort of shocked, like everything was black, or sometimes there was signal, but the signal was very random and didn't find any letters. So my idea was to first, let's try to learn something from the scrolls, then fine tune the learn model on the fragments such that when you go back to the scrolls, there is still some information that the model has learned that it can use to generalize. And this is generally a useful technique for when you have a lot of unlabeled data. I wouldn't say that it was a complete success, but I also wouldn't call it a failure. This sort of approach got me to like the first hints of letters. I'm not sure if it was like 100% necessary, but this was sort of the path I took. And the idea behind self-supervised learning is actually very, very simple. You take an image and you generate two different views of the image. Think of it as, for example, if you have an image of a dog and you rotate the image of that dog, the model should still know that it's a dog, right? Like a dog that is flipped is still a dog. And the same thing for ink. If the image that you have has ink and you rotate it, the ink should be there, or the letter should be there, just rotate it. So the model should learn to represent these two images as the same thing. And this is the whole idea behind self-supervised learning. You do this for different images in the scroll, and then you do like regular supervised training, like in the Kaggle competition. So this sort of got me to the first model that can see some stuff inside of the scroll, and it's a very faint signal. Like you can see the pie, you can see there's some sort of stuff on the line, but it wasn't very clear. And the idea from there was to, okay, let's take this prediction from the model and train the model to be more confident about this prediction. And so I labeled this prediction as well, and I fed it to the model. And you can see that my labels are actually very not accurate. Like there are some mistakes in there. The epsilon, lambda epsilon at the top is actually not really there. But it was like a first step. The model had some idea of what ink is, and this was sort of pushing it in the right direction. And I took this like new label and trained a completely different model. These models like had nothing in common. It was also starting from scratch. And this model actually performed very surprisingly well, and it started to see a lot more signal. And the idea from there was, well, let's just keep repeating the process. Let's label like this new prediction and feed it to a new model. And this sort of kept repeating, and the models kept improving. Of course, in the beginning, the improvements were very big, and then like after the first letters, the improvements were much slower. At the very end, like it was very hard to keep track of what the improvements, but the models were still improving with like the different stuff that were added. So there's a big problem that you run into when you're doing this, which is overfitting. So recall that we're basically training the new model with the predictions of the previous model. So how do you prevent that new model from basically becoming the first model? Like this is what it's trying to achieve, basically, just in a neater format. And you also, like in the labeling process, of course, myself, I don't know Greek. And it's also very hard to know the full context of the words, like what should the letter exactly be, where should the label be exactly. So the labels themselves are quite not perfect. And we don't want the model that basically just memorizes the labels that we give it. We want the model to kind of think about the labels it given. If there's something useful, it learns that. If not, it ignores it. And this throughout like many experiments, this was achieved with a set of things. The first was to actually, after working with the Resna 3D model from the Kaggle competition for a while, I switched to a much smaller model, which is the Inception 3D. I used what's called label smoothing, which is a regularization technique. Balancing the data set also like required a lot of attention. And I used heavy augmentations, but these were basically the same augmentations that were used in the Kaggle competition. And the goal was to give the model some wiggle room to make mistakes. So it can, to some extent, disagree with me. So the Inception 3D, as I mentioned earlier, like a lot of the stuff that came out of the Kaggle competition revolved around video classification. So I went back to the literature of video classification and tried to see like what was going on. And I found that Inception 3D is actually a very good model for its size. And if you know like work in like computer vision, Inception 2D is like very, or like GoogleNet is a very popular architecture. Inception 3D also has this like very weird shape, but it performs very well. And it is a lot smaller than the Resonant 50. I think it's like 1/3 the size, which makes it much harder to overfit. And this comes very handy when you're doing the pseudo labeling, because you don't want your model to overfit before you can get like some good predictions out of it. The second point was high label smoothing, and the idea behind high label smoothing is mistakes can happen during the labeling when you're making your ground truth that you give to the model. This is often not perfect. If you look at like the letter at the side at the right, it might be an O, it might be a C, and maybe the model, when it predicts, it doesn't see like the upper part of the O, and that's completely fine. Or when I'm labeling over the model, I also don't know that there's this part. So when this is given to the model the next time, the model is going to try to learn that this space is actually empty, which is not. This should be an O, and the model should like ignore the fact that it is empty and learn like some signal there. So the model should not be heavily penalized when it makes a mistake. And this is the idea of the high label smoothing. It introduces some noise into the labeling so that the models are not heavily penalized when they make a mistake. And this kind of gives the model some wiggle room to disagree. So when you give the model like this incomplete white label, it can disagree with you and then issue the full O. Balancing the data set was also one important part that kind of controls how readable your predictions are. And sort of, if you have a lot of data of ink and no negative space, the model will just become lazy and predict so much ink, maybe more than there is. And if you have way too much negative space, the model will just become like way too conservative and might also become lazy and decide not to like make a lot of predictions. So finding kind of like a sweet spot of how much data, how much negative space do you take? The way I went around this is I took 256 by 256 window around each letter. And this sort of offered like a nice balance of negative space and ink data. It also sort of at this very sweet spot of not going into another letter, but still being wide enough that it encompasses the letter, doesn't go like into letters in the same row or like in above rows. So I found this to be like a nice spot, and this prevents you from taking like the whole segment, and then you need to sort of introduce negative, false negatives, false negatives into your data. Now, one important part about that came like many times throughout the competition for the first letters and for the grand prize was how do you choose the correct window size for prediction. And for larger window sizes, or if you choose like to use a very large window, this would give the model the full context of the letter. And sometimes, depending on your data, this might allow the model to make inferences that it shouldn't be able to make. Maybe it doesn't really see a signal, but because this shape resembles like all the other pies that it has seen before, it adds like an extra stroke that should not be there, or maybe is not fully there in the data. And so the model can make inferences about data that is, or about ink that is actually not there. The model also learns how to match the label stroke. So it can memorize to some extent like how you draw your labels, whether you do it in Photoshop or in Crackle Viewer. and it can reproduce these strokes. So the predictions, and perhaps you've noticed, for 256 and 512 models, they look quite artificial. You get like a very nice contrast, but they look quite artificial. And smaller windows might actually not have the full context of the letter, or even like the full width of the stroke. So the model is kind of forced to focus on the whatever pattern makes the ink, and this kind of preserves, this mitigates hallucination, but also preserves the stroke shape. And I found that in like the later stages of the competition, it was actually much easier to label the 64 by 64 predictions coming from the model, because it's a lot neater, and it preserves the shape of the letter. And there are some characteristics of how, for example, this scribe used to draw the letters that can kind of even tell you what letter it is, even if part of it is missing. So this was sort of all of the stuff that were done for the first letters approach. The grand prize was really about scaling up and perfecting this first letters approach. And there were two main fronts to be explored for the ink detection. One, how much data quality affects like the data. How can we get like as much data of high quality as possible to train the models? And secondly, how do you train a model such that it makes the most use out of the data that you have? And these sort of processes went hand in hand. And the first scaling up the data, between I think the September and December, there were more than 15 of these like labeling grounds. Each round sometimes explored some new techniques. Sometimes it was just adding more data of segments that have been like added from the segmentation team. Sometimes, for example, I tried some stuff that were not actually good. For example, I remember that for one iteration, after I had like a lot of data, I removed like the label smoothing, and thought, well, I probably now have like highly accurate data. And then I found that some letters like disappeared, and the model wasn't doing as good as before, so I rolled back. So these like pseudo labeling grounds were meant to both explore like how to get the best quality data, and also like to get the best performance, so that it's like a continuous process. One conclusion of this process was that quality and diversity of data actually trumps quantity. So what is quality and diversity? I would say quality is how tight your label is to the prediction. And oftentimes, if you have like a large window size, you might get like very, very large letters, and it might actually be that the letter is thinner. And also like the diversity is when there are signals all over the scrolls where, for example, the letter is not very well predicted, or very weak, or it's only half a letter. And these signals are actually much more important for the model. They're much more informative, because the data that the model already predicts very well do not really offer the model anything new. So you can add a lot of more data that the model predicts very well, and then you don't, or I didn't observe like improvements in performance, where even times when I was being overconfident in the label or over labeling like these weak signals, I would notice improvements in the prediction, because the model starts to become more confident about making predictions in these weak signal areas. The second front of how do you train a model that makes the most out of your data, my choice landed on the TimeSformer. And why the TimeSformer? This sort of also came from the literature of activity recognition and video classification. There's this very interesting paper, is Space-Time Attention All You Need? And basically what the authors did was they did an investigation of all the different ways you can treat the 3D data. And for transformers treat an image like a slice of like small patches, and then as if you like were to slice your image into a couple charts. And 3D attention, or what it refers to, is joint space-time attention, that every patch compares itself or looks throughout all of the patches across space and across time. And this is a very memory consuming operation. It very quickly goes out of memory. very hard to train, but also they discovered that this doesn't offer the best performance. And they tried something different, which is their best performing method is divided space-time attention. So divided space-time attention tries to make that every patch is looking in the neighborhood, in the spatial neighborhood, or not spatial neighborhood, but in the same spatial plane, and then it only compares itself to itself in the temporal or depth-wise. And this makes it so that it's doing like just much less comparisons and much less operations. And at the same time, they found that this scales very, very well. The more data that you have, the more this scales. And this offers much better performance than just looking at everything, because sometimes there's a lot of spatial or temporal redundancies that it doesn't just make sense for every patch to look to all other patches in different times. And TimeSformer scales very well. So this was kind of like the intuition behind why to use TimeSformer. And the first time I trained TimeSformers, I sort of knew that this model was gonna make it in the Grand Prize submission. So for the training details, every training ground started from scratch. So I started with a fresh model with the labels that I have, and I usually only train for 3 to 5 epochs. I found that training for more doesn't really offer you like better performance, and if you train for much longer, you might also would run into overfitting. So overfitting is not completely like erased; it's just mitigated, and if you overdo it, you will overfit. I used 14 columns in training for the final Grand Prize models and 1 column in validation. And I typically used between 1 or 4 GPUs, A6000s or A100s from Vest AI. For the first letters, I actually used Paperspace, which has this subscription-based access to cloud resources because I didn't have a GPU. So that was actually enough until the first letters. After that, I rented like my own instances on Vest AI, but typically you don't really require like a crazy number of GPUs. The models are still relatively small, and you don't need to train for long. And on average, I think like the training grounds took like between 12 and 24 hours, depending on how long I trained for and the amount of resources I put. And one observation that may be helpful to people is that the first epoch results, at least like inference-wise, always look the same for the majority of the models. And it might be actually useful to just train like this first epoch once, and every other time, just start from that epoch and train for 2 more epochs. And I think that should be enough for testing like ideas. So these are the links for the first letters, the pre-training, and our ink detection. You can also find on my website, on my personal blog, there's like a technical write-up that goes in depth, and you can always find me on Discord, and this is my email if you also need it. Thank you for listening, and not sure if we'll do questions before or
maybe let's do questions while they're still fresh.
Yeah. Okay.
So yeah, let's see if someone asked something on Discord as well.
Yeah.
Yeah, I have a question. So, I mean, because you were training it on a specific segment within a papyrus, within a scroll, and there are different kind of scrolls. Do you think that your method is very much dependent on the segments that you have? I mean, the winding number within the scroll, or like the different kind of scrolls? Because maybe there's a different papyrus, maybe the fibers are different, maybe the age is different, maybe there's slightly different ink used, so there are different kind of scrolls. So I was just wondering if you think that the method you've used will also work or the other one, have you already tried out different segments, different papyri? That's kind of my question.
Yeah, thank you for the question. So okay, let's break it down for this scroll and then for other scrolls. I think that for this scroll, I think the model actually works very well throughout the scroll. So I tested the model near the air gap, which is a bit further from where the 15 columns were, and the model performs quite decently. And I think we also had like a very exciting finding from tomato segmentation, where we had like the last or before the last winding of the scroll, and there was still traces of ink there. So I believe that, of course, the model was not trained to handle like these harder areas, but it still like generalizes, and I think this is like something to explore further this year. But I'm confident that for scroll 1, I think we have like really good models. For other scrolls, there are still some issues to be solved. I think that it will be solved, that this approach could be made to work for other scrolls, but it's probably not there yet. I tested like the model in December on scroll 4, and it didn't work, but it was different than when the models didn't work at scroll 1. Now the models like see a lot of different patterns, and it's the question of like trying to figure out the right patterns to target. There was like some interesting finding that I don't know if I'm allowed to share it or not, but there was like a joint project here in Berlin and working on like Egyptian papyrus, which is like different era, different place, different papyrus, and the Vesuvius models actually can find like some traces of ink on this papyrus, which I think is telling of the generalization ability of the method. It's not there yet, but I believe it will be soon.
I can ask another question. Your models, is it possible to actually feed your models with a Greek alphabet and maybe with a Greek dictionary? Do you think that will improve things, or do you think that it will start just making up random texts?
I think that at least for the Vesuvius challenge, it's kind of not encouraged to do so, because this interpretation, like when it's done by the model, you're then left, when you're reading the text for the papyrologist, you're left to like fix first the mistakes that might come out of the model or the hallucinations, and then try to read the text. And this kind of creates unnecessary dependency when there are like experts who can read the text. It might be useful like in later stages where some like areas, for example, are damaged or too hard to read. Perhaps then it could be also like trained with the priors of the Greek alphabet. I believe that in the Kaggle competition there were attempts of like training on letter shapes and stuff like MNIST, so that the model kind of has like a prior of how things should look like, but it didn't like it wasn't fruitful. I also tried it and wasn't very impressed with the results. Might be useful like at later stages, but I think for the moment being, like smaller windows sort of give you this authentic stroke where you can like see the scribe handwriting in them.
Okay, there's another question from Aaron Wayne. Do the models at this point ever predict letters where the human eye doesn't see anything at all? Or is it pretty much enhancing signs of what a human could see with enough time?
Yeah, so this is actually a very good question. I think like we haven't spent much time trying to analyze the signal. The main idea behind like the pseudo labeling process was to avoid looking at the CT scans, because they're really hard to look at. But I think there are some areas where it's very, very hard to figure out what the model is seeing. It's clearly seeing like the correct letter and it makes up the correct word. but it's very hard to, like, with the naked eye see what the model is detecting in there. There are some areas that are fairly visible with Crackle, but some areas at least myself, like, I don't have an eye for it, so it's really hard to figure out what the model is seeing. Yeah. Yes, Tom.
Sorry, I have one more question. I mean, obviously, first, if you have to scroll, you have to scan, and then you have to virtually unroll it, and then you run the models. The quality on the unrolling. I mean, how much does it affect your work? Do you think that at the moment the segmentation, I mean, how it's done at the moment, it's, let's say, near perfect, and really that's all you can work with? Or do you think that no, I think we should be able to do much better in segmentation, and then the models will just put them in once and they find everything? I mean, do you still have hope that there could be much better segmentation, a way of doing it?
Yeah, so I would say that actually segmentation, or at least manual segmentation, is at a very good spot. I think also automatic segmentation is almost there. We did a couple of experiments where we tried to resegment areas ourselves where the signal just dies. And oftentimes we found that, for one, this doesn't always improve, or very often it doesn't improve. Improvements are usually very, very, very small. I think there was like a recent segment from David where it's 4423 and 4424, where the very, very high accurate segmentation actually does reveal a little bit more signal, but it's not like a drastic like change as you would expect. I think there are also areas where the segmentation looks very, very well done, but the model is still not seeing the ladder, which may show that either like the signal itself is damaged, or there's some signal that the model is not yet picking up. For like the follow-up from Aaron about the smaller context sizes, I'm actually not sure that there is like much difference in that regard between the smaller context and the larger context models. Yeah, I don't think like we've tested like this with respect to the context size as well, but I think that the smaller context models make it easier to label and are less prone to like producing artificial strokes, which make it like easier to see like the letters. But I think maybe yeah, I don't think I can give like a concrete answer for this.
I have one more question on the resolution of the scans. I mean, I think at the moment they are at quite high resolution, the highest that you can do, as far as I understood it. If it were possible to actually have even higher resolution with the scans, do you think that that your models will actually find more letters or faster, or that the signal is clearer, or do you think that a certain cutoff where you think, well, even more resolution is not helping more? I mean, if you disregard obviously the speed and the memory usage, I mean, just do you think that more resolution will make it better?
For more resolution, I think there is like we need to make this jump where we have also labels for, or we have something labeled at higher resolution and lower resolution so that we can compare. I think there are some signals that might be improved with higher resolution, but I also think that, for example, scroll 1 could have possibly worked in lower resolutions, or models will be able to generalize to some difference in resolution, not like very, very huge, but to some extent they will be able to, if they see something in a certain resolution, they'll be able to, with some leeway, see some signal in a different resolution. It's still to be seen, like how much of a difference and how much can be preserved, or needs to be, how like high resolution is needed so that we can like read the whole thing, or is the signal actually not there? So no matter how high you go, it's not going to improve. I think this is like one of the questions for this year's challenge. But it's very exciting to see where it goes from here. Yeah, I think if there are no more questions, we should move over to the presentation from Julian.
Okay, yeah. Thank you so much, Youssef. Very well done. Okay, let's share my screen. Can you see the presentation?
Yes.
Okay, perfect. Also a welcome from my side. I was more focused on segmentation. I also did some ink detection, but I was mostly doing segmentation. Well, a little outlook, why segmentation, and then I'm going to present last year's segmentation algorithms and what I'm working on right now, mainly Tato. When I started with this project, I guess quite at the beginning, I also started with ink detection, and there I developed some algorithms which I was quite happy with, but I wanted to test them in the scrolls. And the only segmentation that was able to find was volume cartographer. And so I downloaded it and I was sorely disappointed. It wasn't working at all. It was very clunky. It was very slow. It crashed often. Yeah, and you could only produce extremely small segments. The segments were the maximum possible segment size was maybe half a letter in size, so nothing that I could use. And therefore, I went on and created some improvements in volume cartographer. Mainly, I started with a segmentation algorithm. That's like the workhorse of this tool, which propagates where a slice is in the 3D volume. And there I had this idea. When you look at videos, there is this problem called optical flow, where someone tracks a pixel from one frame to the next. And actually, a video isn't that different from our 3D scroll volume. If you take 2D slices and move through them, like in this video here, then yeah, you can see it's quite like a video. So I could use optical flow and sometimes track those sheets well. To go a little bit more in detail, those sheets in this volume cartographer short VC are just tracked by having a curve made out of points on this sheet, and then the computation takes this curve into the 3D volume. Yeah, so I started with optical flow, calculated the difference, movements difference between frames, and then just used those to update the location of the points in the curve. This worked quite well, but after some back and forth with someone in the community that already did some small segmentations, I just offered them to use my tools. I wanted segments, so I just told them, you can use my tool, but please give back to the community the segments that you create. And Harry was happy to do that. So I got some feedbacks, and I did lots of iteration and testing and testing and testing to make this tool well and working well. Some intuitions also, I smoothed the curve out after propagation. You can see the scroll is white and the background is black. So if a point of the curve moves into the black regions, it probably lost the sheet, and you could try to move this point back to the bright sheety area again. There are two things that I focused on when improving volume cartographer and optical flow segmentation. One was the algorithmic side. So these algorithms, they took a long time, and it was really time intensive just to wait until your algorithms moved up a millimeter or so through the scroll. So I made the algorithms a lot faster, and I also made them more accurate, so following the sheets better than the ones before. Faster access to the volumetric data was also a big thing that one has to have in the back of his mind, because else you just wait until the data is loaded. And then I also did some performance testing on this code, and I found out that the curve calculation, the mathematical representation of this curve back under the hood of Volume Cartographer was very slow. So I optimized that, and that alone gave 100 times speed improvement. So crazy numbers there. Also, the second avenue, the second branch, was the manual work that went into it. If you had less adjustments, if your algorithm was more precise, you need less work, and the manual segmenter could maybe run 2 instances of your computation at the same time, and yeah, just get more done, more segments. I also made it easier to navigate this tool, to adjust those curves. You just now can click where you want the curve instead of actually dragging those points to the right position. And also added tools to have the segmenters be able to also at least somewhat segment mushy areas by adding multiple lines that they could display, maybe the sheet in front and the back, and then they could maybe infer where the middle sheet is. Yeah, reducing crash frequency, big bonus, so that you don't get discouraged. Yeah, so the main reasons for success for OFS are probably that it was an interesting problem. This segmentation problem was very interesting to me, and I had the grits to stick with it. And then after that, Volume Cartographer was already a little bit used, so I had a user base, and their hair were burning because they had such bad tools, and it was the only tool, so they were happy for every improvement and every test they could run with the hopes to get something better. It was developed in the open, so everyone had access, and I got a lot of feedback from users, which led to fast iteration cycles. And there was also a quite nice performance tracking ability. I just looked at how much sheets the segmentation team output, and then I knew how well my algorithm does. Something here to note maybe is they went for the easiest parts first, and then they went for the harder parts. And then you can see where so here I steadily pushed new updates, and then here I started working on Tato, and then around here I pushed some updates again, and and then it increased a little bit again, because yeah, the harder the segments get. And yeah, some of the reasons. There are certainly also others. So if you track like how well you could extract sheets, in the beginning it was single-digit square millimeter sheets that you could maximally extract, and then in the end it was hundreds of square centimeters for a total of over 2,000 square centimeters of sheet area. And if you just calculate how much improvement that is to the algorithms, it's around about a 10,000 time fold improvement. So VC is quite clunky, and it's really hard to work with it, although I think it still has lots of potential also this year to get better algorithms going in there. So I could highly recommend you, if you have an idea, try testing it there. The user base is there, and I think there's a lot still possible. But I decided I want to segment whole scrolls, and even though 2,000 centimeters is quite an impressive number, it's still only 5% of one scroll. And if you see that it costs more than $100,000 to do it, well, we are not able to segment like that for much longer. We need better algorithms. We want to segment at scale. That's my goal. That's why I started Tato on a corrector. I wanted a clean start, and where I could apply the learnings I did from my last project. And I formulated a battle plan. Mainly, I want to build a pipeline where I have smaller sub-problems that I could solve and test and just flip out, that solve one problem after another, so that I can go from the CT scan directly to the mesh, which then can be used to generate a surface volume and just do int detection on it. So there are 3 big things that I focused on. when developing this. First was, or also designing, mostly designing. I want it to be generalizable. I want to have as much abstraction as possible because the data is so huge, and if you just reduce the amount of data, you also reduce the compute most likely. And just abstraction generally is a very good idea in this type of situation where you have this much data and lots of it is not important to your problem. And lastly, for segmenting at scale and with reasonable prices, we need as much automation as possible. So yeah, those are the 3 design principles that go through Tato. So here, a small overview of the pipeline. First off, maybe not part of the pipeline, but still is this user interface where a user that doesn't really have a lot of knowledge in how to use the command line or scripts and start them. And yeah, well, you have lots of different parameters that go in those scripts. They can just use this user interface and yeah, just press a button and the computer computes whatever they want. And then the pipeline really starts with grid cells that get generated at the right resolution. From there, we extract the surface points, which then form a point cloud that just like shows the surfaces of this scroll. And well, we can see it at that point, but the computer just sees points. So we need to somehow, again, get the connectivity information in there, which we do by extracting small sheet patches. We then stitch them together. And in the last step, before we have the mesh, is meshing and flattening the mesh. So make it from a rolled up state into a flat state. And at that point, it can be rendered. Yeah, I also implemented some fast rendering to actually be able to debug more quickly what is going on. So the user interface looks like this on the right side. You have this flow again from the computation. You start at the top and then you work your way down. And something that I haven't seen so far was this umbilicus that I'm generating. This is something general, so you can do this for every scroll. It looks every time a little bit different, but it's the center of the scroll. So this is where you wind around your papyrus sheets. And yeah, you can start it with this command Python 3 tamato.py. Then you get this. Generating this umbilicus can be done here under this setting, where you just press generate, and then it brings up a graphical user interface, and you just press up to the middle of this scroll. It takes like 5 minutes. It's really not that work intensive, and then you have it for a scroll. I would just suggest doing it that way because otherwise it's quite hard with all the transformations that the scroll undergoes in the coordinate system to get the scroll, this umbilicus at the right position. So yeah, you first need grid cells, and they need to be at 8 micrometers. That's done because if all the scrolls are at the same resolution, or you just downscale it, then you have something general. It looks a lot simpler, and next steps happen a lot faster. Yeah, you don't have to take into account different resolutions. You just, yeah, downscale. And grid cells at the time were a very easy volumetric access data format. It's still quite good. So there's also this blocking. You will have grid cells. So a cell is a block. It has 500 by 500 by 500 voxel size, and it contains this area's information. So this blocking is something that I kept, and I went through it in most steps, because this blocking is kind of splitting up the computation. It's in smaller parts that you can handle. Those scrolls are terabytes of data, and those blocks are hundreds of megabytes. So the first step now is actually to extract those point clouds, make this more general, get rid of all the noise in the CT scan, just to get a representation of this problem that's more compressed, uses less data, and it is also easier to analyze. So here you have a side view on the left, and the top view on the right, where you just have like a slice through this scroll, and you see those sheets. You can see them here. I also have some of them marked here. So those are sheets that you can see here. Those worms are sheets. So this is a slice, top view slice through the scroll, and this is a little bit from the side, and also only a little bit. You can imagine here is also scroll volume with lots of points. If you would just display this whole scroll, it would just look white because you have a lot of points. And also, sometimes you have to have the right viewing angle to actually see those sheets nicely, like here. Over here, it's just mush, but that's not because there's mush, but just that the angle at which the sheets are with respect to our view plane is different. If you would rotate it correctly, you would see it the same as here. And yeah, those are the blocks. For the computation, those blocks, they are 200 by 200 by 200 are side lengths, so a little bit smaller than before. And yeah, so intuition, how to create those sheet surface points and how to extract them. If you look at this sheet on the right side, the sheet is so bright and the surrounding is dark. And well, if you just plot this intensity, it kind of gives a Gaussian curve. Maybe you blur it a little bit to get a better curve, I don't know. And so the really important points are those red dots here. Those are the inflection points of this function. They are quite easy to calculate. You just so let's say here's the front and the back. You see the first derivative here is at the maximum and here at the minimum. And then so the second derivative is both times 0. So you actually even can distinguish front and back side by which sign the first derivative has at this point. You can just threshold first derivative over a certain threshold, the second derivative close to 0, and that's how you can extract those points. To go a little bit more in detail, to have it a little bit more technical for those that are interested, there are a few things that we do here. So the abstraction, generalization, I already mentioned. Then 3D image analysis. Well, there is a Sobel filter that actually kind of does this derivative analysis in 3D that I showed you here in 2D. And we also have this the scrolls. So the 3D analysis kind of gives us the normal of each sheet. Then, like here, the normal would be in this direction, and here in the opposite. If you just take the umbilicus position in the scroll and those normals and flip all the normals towards the umbilicus, then we have like a nice, good representation. And because of how this CT scan was acquired, it also has noise. So we apply some smoothing there, and that gives a better estimate to the local sheet normals. With those, the problem can be abstracted again and put down into this 2D final form, where we go along the sheet normal at each point to extract down then those surface points. Also, yeah, easy to distinguish front and back, so they can be saved, yeah, at different positions in the data. So later on, you still know which side the point belongs to. To some degree, I found out that if I just take the CT scan and do those analysis on it, you have a problem on the edges. There, the derivative analysis get off, and it gives some wrong points, just some flat parts at the edges of the cubes. So I actually do a padding to the CT scan. So I take a 300 by 300 by 300 voxel image from the CT scan, and then I generate the point cloud of size 200 by 200 by 200. So cutting away these padded things. The computation, I lately also made multi-threaded and multi-GPU capable. So it's quite fast in the sense of, for a whole scroll, you probably need 1 day to compute it on a 8 GPU system with A100s. So yeah, kind of fast thing with this pipeline always is it takes a lot of compute. Here you can see the files that are well, that you could go check out on my GitHub for Tato. Yeah, and here you can see how those one of those blocks look like up close. You can really see those points. And here I did some work and actually extracted some of those point sheets, and they are quite clean. And well, that's one idea now that's quite close. Well, those sheets, I can extract them and see them manually by eye. Maybe we can also train a computer model that does it. And that's actually a problem that's well known, and there are it's an active part of research, and it's called instant point cloud instant segmentation to extract one of those sheets. So yeah, human can detect it. Well, let's automate it, design principle and so on. That's the name of the thing. And then, well, there are lots of different models that do point cloud instant segmentation. Our instances have their centroids, their center point quite close together. So we have to be a little bit more careful which model that actually is appropriate. Mask3D and how it extracts its instances is appropriate. So I picked that model there. Yeah, so there are two avenues to training data generation. I was a little bit lazy. I didn't want to annotate that much, so I automated synthetic training data generation. I also did a lot of variation there, so to simulate different scrolls so that it is also capable to, if only, segment different point clouds from different scrolls. Well, the generalization of going from CT to point clouds already did make the data look quite a lot similar between different scrolls. But yeah, adding some more variability in the training data is good as well. And then I also annotated 60 blocks of those point clouds from scroll 1, and also added them to the training set, which I then used to train Mask3D. And with this trained model, I then could do instant segmentation on the whole scroll, which also is multi-GPU capable, and on the same system, again, takes half a day to a day to actually go through the whole scroll and predict all the patches. For each block, I'm going to save my predictions into a .tar file, and each surface has a .py file in there. To actually then use the connectivity information and not just have blocks adjacent to each other, I actually let the blocks 50% overlap to later on then combine those small patches. They are only around about 0.5 millimeter or 1 millimeter in size into larger sheets. And this is how ChatGPT imagines this patches staging problem. That's I think it's quite a hard problem, and how I go about it, and I think there's lots of research still needed there, is you have those patches which kind of are like a node in a graph, and the edges between the nodes are how much adjacent or overlapping patches actually overlap. So how many points are the same in two adjacent overlapping patches. And so the connectivity is kind of this number that can be computed, and then I can build kind of like one of these graphs where you can see the spirals are just the windings of the scroll, and sometimes the scroll has bad connections over here, for example, between different windings. And this also happens in real life because those sheets, sometimes they fuse and the point clouds fuse as well. And the model doesn't really know which point belongs to which surface. You have to imagine here, maybe nice to design here as well. We have winding numbers, so you start in your center where your umbilicus is, and then you just count how many times the sheet goes around the umbilicus, and then you have a winding number or a winding angle. So maybe here you have winding angle 0, then here it would be 360, 720, and so on, as you go outside. I tried, building this graph is quite cool. I think that's the right approach. But next step is to find a good subgraph that actually doesn't have those wrong connections in there. And there are lots of approaches that I tried, and I've learned lots from each of those approaches. I started by dividing and conquering, but quickly stopped with that because it uses so much compute. Those nodes, you have to imagine, one of the graphs for scroll 1 has over 1 billion edges. So divide and conquer takes a long time, and it doesn't really give good results. So I stopped that one. Then I was like, yeah, let's just extract smaller sheets. Smaller meaning like tens to hundreds of square centimeters. And I started with doing greedily just picking the best edges that are connected, which resulted in lots of sheet jumping, where the algorithm jumps from one sheet to the next in your final mesh that you extract, which isn't really nice because you want to read the data. But it already showed that the points are accurate, because if you then reconstruct from the point clouds a mesh with meshing you and then render it, it actually showed that you could see the papyrus surface on it. So I was quite happy with that, and I iterated on it and arrived on random walks. There I will come back to later. Yeah, I tried lots of different approaches as well that didn't really work out, and right now I'm developing evolutionary algorithms that evolve a subgraph that fits the criteria. So yeah, let's look at the random walks here. This is a small sheet that's extracted with random walks. It looks quite cool, and yeah, that's how those windings around the scroll look like. And you have to imagine in this graph, you just take a starting node, and then you just randomly select the next node to walk to. And sometimes you go around the umbilicus, and then you have you add a winding number to your node that you are at every time in a winding number. And if you arrive at the same node again and the winding number difference, you probably went around the scroll and switched your sheet. So that's a bad walk. But if you arrive at the same node again and it has the same winding number, it's a good node, a good walk. And then you just add up all the good walks that you make and on loop closures, and just count how many good walks are per node. And if you reach a certain amount of good walks per node, you actually add that node to your set. So here, that's the surface point. So maybe this walk consists of maybe 100 nodes or so. So after you have extracted those surface point clouds, where you now have, instead of a 3D point cloud, you have a 4D point cloud. Also, the fourth dimension would be this winding number, this winding angle. You now can generate a mesh from it. And doing that, what I started doing is using half a winding and doing Poisson surface reconstruction. Then doing this on every half winding and stitching the sheets back together, the meshes, gives you this rolled up scroll mesh. Then unrolling it happens with Slim. And big thanks to Giorgio. That was one of his contributions, and it's a really cool algorithm that he found in the literature and applied to this problem. But the problem is this Poisson reconstruction produces non-manifold surfaces, and those are hard to flatten, and even Slim cannot flatten them all, and sometimes, or lots of times, fails. So it's kind of a gamble if you get out a good segment or not. And using the random walks, which are okay, but depending on how hard the segmentation is, switches sheets still between once every 10 square centimeters to once every 100 or 200 square centimeters. There's still lots to do there. So yeah, those two are areas where I think most improvements could be made. An idea is maybe get rid of Poisson and actually do the hard work and do the meshing with an own algorithm that was implemented, or maybe someone has an idea how to do it properly and how to get manifold surfaces. And the last step, rendering, it was really slow using VC render. So to speed up development, I developed a better rendering technique. Here you can see how it renders in real time. Well, actually 4 times speed up, but still it's quite fast. And yeah, you can stop it if you see that your mesh that you created was bad. So this is something I hope helps a lot of people while developing segmentation algorithms. And you can save your stuff in lots of different output TIFFs, JPEGs. Something very interesting about JPEGs that I found out is you have TIFFs use a lot of space, and JPEGs are, well, better compressed. So they have like a 20th of the space that it uses. And actually the surface looks quite similar, and the ink prediction on our Grand Prize model also virtually detects the same ink. So there's probably a lot of potential, not using the whole data, but actually using JPEGs for the surface volume. This tool, again, is multi-GPU capable. This is one of the Grand Prize segments. It's 336. It uses around about 12 hours to compute on with BC render, and yeah, well, 100% speed up. Here it renders in around about 6 minutes. Yeah, that's one thing. So here, yeah, that's the script that you can run to use it. And then here from Tato segments and the ink predictions, how it looks like right now. And yeah, it's only getting better. And we hope it's soon at the stage where it's readable. Also, to say, I don't have those here, but every letter counted, and sometimes actually in the Grand Prize segmentation, I did some resegmentation of those sheets that were used in the Grand Prize ink banner. And at a few points, actually, resegmentation with Tato yielded better letters, or letters that weren't readable in the main segmentation. It was like, I think, a tau at one point. But yeah, it's mostly verse, but at some points it was a little bit helping. So yeah, every letter counts. So limitations, lots of it. This sheet switching is one of the big ones that has to be solved. I'm right now, yeah, I forgot about that. Right now I'm implementing evolutionary algorithms there. Those are mainly evolving. Like I can detect if a graph is bad, right? If those winding numbers are bad, don't match up for a node. And those can kind of be used as a fitness score. And I then evolve a model that selects edges and by evolution, and just gets a reading back how good its fitness is. And on small problems, this works surprisingly well. It's really good, but the problem with evolutionary algorithms is that they scale pretty badly. So doing it on a scroll volume size is kind of a challenge. I think by subdivision, again, with divide and conquer maybe, and contraction of the graph based on suggestions from these evolutionary algorithms, it might be actually able to solve the problem well. And that's my part that I'm working on right now, to solve this sheet switching. So one other thing is this coordinate systems that are used in Tato. They change from one iteration to another, or just from one script to the next. In the beginning, you have your scroll coordinate system from the grid cells, and then it flips and adds 500 to each axis. And after that, it's getting shrunken down by a factor of 4 when the sheet instance predictions happens. well, yeah, there's there's something to be careful about. Just go see the documentation PDF for Tato. Those are explained there. Generating non-manifold meshes with the meshing that's implemented right now is a problem. Manifold meshes probably are the way to go instead of getting better flattening. But either works. Maybe someone has an idea, and lots of compute that is needed to solve to actually solve this segmentation problem. But overall, I'm pretty confident that it's something that we're gonna manage this year, and I hope to see lots of you doing it as well with me. I'm happy to have any conversation about it, also in private. Yeah. And this is my presentation part. I wish that you learned something. And yeah, if you have questions now. Okay.
Yeah, if no one else has a question, I'm asking one more. So I was just wondering, because it's segmentation, so effectively we are dividing up the problem into segmentation problem and the ink detection, and they're completely separate from each other. Yeah, and there's no feedback from the one to the other one on interaction. So I was just wondering if you detect, like, the first letter that was detected was just pi, yeah, and if you actually try to adjust the segmentation algorithm in such a way that the pi becomes sharper. So in a sense, you're using information from the ink detection algorithm to actually maybe fine-tune your segmentation algorithm. And then once you have fine-tuned it, then maybe use that segment, the segments that get produced, to actually detect the ink. I'm just wondering if it's possible to have an interaction in between the two exercises.
So right now you're right. There is not much overlap, so no feedback loop like in Youssef's labeling. But how I use the ink predictions are just to verify if the segments that I produce actually are good enough to detect ink. So for the quality of the segments, I thought about using ink prediction, but when I started, there wasn't lots of ink prediction out there, and lots of position in the scroll actually doesn't, like, let's say scroll 3, for example, doesn't have known ink in it yet. That's public, which gives gives a problem that this wouldn't work there, and I haven't found a way to incorporate it yet. So right now it's not done, and I don't know. Maybe you could sometimes maybe you could have your mesh do ink prediction on it, and then move the mesh a little bit in either direction and do ink prediction again, and see if the detections are getting more accurate, and like that refine the mesh. But so far not implemented. No.
We have a question from Santiago. When a random walk closes a loop, is that loop closed with a separate routine or by more random walks?
So you start lots of random walks, you spawn millions of them, and you just look at the nodes that you already know which winding number they have. So nodes that are actually already selected for your subgraph. And as soon as it reaches one of those nodes, it closes and checks if the winding number matches. If it matches, it's a good walk, and if it doesn't match, it's a bad walk. And yeah, you start from known nodes as well. You don't start from random nodes. Yeah.
we have another question that's passed from Discord. What kind of difference between scroll 1 and others is probably the reason to affect the model performance? Any guess? I guess this is for the ink detection. I think that for one, like there's a difference in the crackle distribution, or there are more cracks in other scrolls. It's hard to like determine which are ink and which are not. And there is also a difference in the intensity of like the scans. Yeah, I don't know if there are like other differences that are contributing to the difference in performance. Might also be that the letters are a different scale, but yeah, this is not sure. But I think there's like the model like sometimes finds if you run, for example, the TimeSformer on scroll 4, you find like it's like lighting up in a lot more places than there should be. Like it should be less ink than this. So that's one thing. There's another question. Did you have a single big aha moment with Tomato using the umbilicus, for example, to guide the winding process, or would you say it was mostly incremental?
I kind of went at it from a mindset like when you play chess. So you have your strategy and you have to have those parts fitting in together. I would say the biggest aha moment was when I figured out how to look at those sheets with the sheet normals and extract the sheet surfaces. This was quite cool. And then I strategized around that and how to get somewhere where I have a general solution to the problem. So can you comment on how Tomato does on each of the scrolls? Scroll 4 look easier than scroll 1. Scroll 2 looks much harder. So I've run the point clouds processing on scroll 1, and locally I'm using scroll 3 to develop it. And also I've looked into scroll 2. Just this week I sent some point clouds to Josie, and he looked at it from with Cartes. There's a script where how you can get the point clouds that I extracted back into Cartes, and the points are looking very clean. They lie on the surface very well, also in scroll 2. And if you look at those points, it looks quite a lot similar to what I shown in this one slide, where where you just see the surface in the scroll. So I don't think that scroll 2 will be much harder than scroll 1 or 3. Scroll 4 probably is the easiest because you have lots of space between the sheets and probably less chances to go switch your sheets. Maybe I haven't tried it, but maybe Tomato in its current form is already capable of segmenting it. Yes, but I have no idea. How sensitive is point generation? Can it generate between touching sheets sometimes? So mushy areas, yes. I'm not sure about completely compressed areas, but mushy areas, yes. Then you would have you have enough information still to actually humanly see the different sheets, and the algorithms also is able to create patches that follow the sheets. The instances are good enough. Probably to get the accuracy up even more, you could add more training data, label those difficult parts for the point clouds, and add it to the training set and rerun training. For the training of Mask 3D, I would just recommend using the checkpoint and training from there, adding more data and just training from there. And scroll through looks nice in the point clouds.
Yeah, Yeah, I was asking if it. I was in my first question. I was asking if it's possible to use the ink detection to inform the segmentation algorithm. Now, I mean, if you look at the scrolls, obviously you also have other information inside of those images. You have the papyrus fiber structure, for example. I mean, and obviously, if you do the segmentation, it's useful to have a coordinate system. And usually you have an abstract coordinate system that you lay on top of something. But of course, here, in a sense, you have a physically implemented coordinate system, which is like the fiber structure with the vertical fibers, and you have the horizontal fibers. I'm just wondering if it's not possible to use that kind of information, because kind of the segmentation algorithm, at the end of the day, needs to output something where you have horizontal lines and vertical lines from the fiber structure. So I'm just wondering if it's not possible to use that kind of information, or maybe detect those lines and then kind of feed it back to the segmentation algorithm.
Yes, I think that's a good idea and a good approach. I also saw some 3D labeling or extraction of papyrus sheets from the community. So some of the people are pursuing this avenue by extracting those fibers and then maybe building up the coordinate system like this. But I guess the problem that I came and run up against is you can get like lots of things you can get to work 98% or even 99% of the time, but then at some points it just fuses two sheets, and maybe your algorithm detects one of those strands going from one sheet to the next as well, and you have this problem of fused sheets. The data is not very clear at some points, and those 1% of mistakes, how do you get rid of those is the big question. How to filter them out. I hope, did it answer your question, Tom?
Yes, yeah. I mean, obviously, it's always easy to come up with a good idea, but of course, execution is 90% of the.
Yeah.
I was just also there. I also saw in some pictures, I saw very bright dust particles. Yeah, that somehow got into the scrolls. I don't know what. I'm wondering if those dust particles can help us in some way, or I mean, when you look through the thing, did you notice a lot of these dust particles? I'm just wondering if that's.
So it depends on the scroll. That's really scroll dependent. I guess it's mud. I don't know what exactly it is. Sometimes it's really a pebble sized stuff between the sheets. Sometimes it's like a layer of wet mud that went and just dried up on the sheet. I have no idea what exactly it is, and it depends on the scroll. Sometimes, yeah, you could maybe use it to inform which sheets do not belong together. You could maybe cut away some of those bad connections between sheets with that. But probably this mud is in places where the sheets aren't fused in the first place, because yeah, otherwise the mud wouldn't have had space there. I don't know, the crackles sometimes also are a little bit brighter, maybe because more mass is at that point. But I really don't know what exactly it is, and it's highly depending on the scroll. Okay, so if everyone, let's see Discord again. I think otherwise we're at a good point, I guess. And thank you very much for attending. It was a pleasure to talking about it. And yeah, hope to see you around as well.
Yeah, thank you so much. And if you have more questions for us, you know where to find us. So yeah, feel free to reach out.